In this module, we zoom in on what happens after a wallet presents credentials. You'll see how we verify the signature, confirm the issuer is trusted, check status like expiry or revocation, and classify errors so the final KYC decision is defensible and explainable. You've already moved from big-picture eIDAS and wallet concepts into the gritty details of compliance, architecture, and protocol flows. Now we're focusing on a critical question. When a wallet sends attributes, how does a relying party decide whether to actually trust them? We'll connect verifiable credentials, OIDC flows, and governance to the relying party's risk, fraud, and verification checks, setting you up for the Azure implementation work that follows. A verifiable presentation is just raw input. To make it decision-ready, we run it through layered checks. First, we validate the cryptography, schema, and attribute formats. Then we evaluate issuer trust, revocation, and status. And finally, our own KYC policies. Each step can pass, trigger a manual review, or block use of the data. And at every step, we log the outcome. So later we can explain, troubleshoot, and defend each onboarding decision. Think of a relying party verifier as a stack of filters. Protocol validation checks the request and response shape, nonces, audience, and redirect handling. Cryptographic validation proves the signatures, algorithms, and keys are sound. Trust validation asks whether we actually trust this issuer and credential type. And business policy validation enforces what your organization cares about: age limits, jurisdictions, freshness, assurance levels, and KYC rules. Signature and integrity validation is your first hard security gate. Start by verifying the digital signature or proof using the expected public key. Confirm that every signed claim matches the protected payload. If a field isn't covered by the signature, treat it as untrusted. Enforce an allow list of algorithms and reject weak or deprecated ones. And finally, make sure the proof is bound to this transaction with the correct nonce and audience. When you verify a signature, the first question is, whose key am I actually using? Key resolution means retrieving the issuer's public key from a trusted source, like a DID document, JWKS endpoint, or certificate chain, and treating that metadata as part of your security boundary. You must confirm the key ID, intended usage, algorithms, and issuer binding, and defend against stale metadata or malicious key substitution. That means cautious caching with clear expiration and refresh rules. Binding a presentation to a specific request ensures every response proves it belongs to this exact session. The relying party issues an authorization request with a nonce, state, audience, and redirect URI. The wallet signs and returns a presentation referencing those values. The verifier then recomputes. Does this response map to that authorization request within the expected time window and transaction? If anything mismatches, it's treated as a replay attempt and rejected, and a security log entry is created. A valid signature only tells you the credential hasn't been altered and came from a specific key. Issuer trust validation asks a different question. Is this issuer allowed to make this claim for our KYC use case? You check trust registries, certificates, or metadata, and compare the issuer's role and assurance level to your policy. Always log signature valid separately from issuer trusted, so decisions and errors stay clear, traceable, and auditable. Every trust model needs a primary source of truth. Trust registries let an ecosystem publish who is allowed to issue what. Certificate chains rely on PKI routes and intermediates to validate signatures. Federation metadata shares signed descriptions of participants and their endpoints. And local allow lists apply your organization's risk policy to issuers and schemas. In practice, you'll often combine these, but whatever you choose must be explicit, maintainable, and fully auditable. Even when a credential is authentic and from a trusted issuer, you still need to know if it's valid right now. Compare its expiration and not before dates to a trusted time source. Then check any status service to see if it's revoked or temporarily suspended. Treat revocation as permanent invalidation, while suspension is a pause. Finally, decide whether your system fails open or fails closed when status services are unavailable, based on your risk tolerance. Status checks always sit in a tension between freshness, availability, and privacy. If you call an online status endpoint for every presentation, issuers or intermediaries can learn where and when a credential is used. To reduce correlation, you can cache status lists, use short-lived credentials, or design anonymous privacy-preserving protocols. Whatever you choose, log and store only the minimum evidence that validation occurred, and align with privacy by design and GDPR expectations. When everything is just an error, you lose control of both user experience and operations. This taxonomy gives you 4 different playbooks. If the user caused it, you focus on clear messaging and simple recovery. If the request or format is bad, you fix validation and compatibility. If trust or security fails, you lock things down, audit, and investigate. If infrastructure breaks, you alert, fail over, and retry. Same failure surface, very different responses. Let's ground that in 3 common failures. If a user just cancels, give a friendly confirmation and maybe offer a different path, but don't treat it as an attack. If the issuer looks untrusted, show a generic failure, silently flag it as high risk, and push details to fraud monitoring. If a status service is unavailable, explain it as a temporary problem, suggest retry or alternate credentials, and log rich diagnostics with a correlation ID for support. Every validation run should leave a clear, minimal footprint. Record what was checked, the outcome, the policy version, and a correlation ID that ties the decision to a specific customer journey or case file. Instead of storing full credentials, keep evidence references and timestamps, so auditors can reconstruct what happened without exposing extra personal data. Then align these logs to your compliance matrix, so each audit trail supports a specific AML or KYC control. You've now seen how protocol messages become real onboarding decisions. Signatures give integrity, issuer trust makes them usable for KYC, status checks keep them current, and disciplined error handling keeps users, auditors, and operators aligned. Next, we'll turn these principles into concrete Azure architecture, security, privacy, and operations.